Hi, welcome to my basics on geomathematics. In this course, I will talk about polar coordinates in 3 dimensions. Certainly, these coordinate systems are not only relevant in earth sciences, they are also relevant in many other applications where you have spherical structures or where you have a rotational symmetry involved. I will tell you how these coordinates can be constructed, how they can be understood, and I will give you some basic tools that are usually helpful in many applications. Before we have a look at polar coordinates in 3 dimensions, we will have a look at 2 dimensions. First of all, we start with a 2-dimensional sphere, also known as a circle line. And you might already know how this is parameterized. You say that the points, I would say, now x1 and x2, you can say also x and y if you wish. They are parameterized by cosine phi or and sine phi. This is how you parameterize a unit circle. If it has a different radius, you put a radial coordinate in front. So certainly by that, you can describe every point on the 2-dimensional plane with coordinates r and phi. If it's not the region of the coordinate system, if it's not the 0 point, then these coordinates r and phi would be uniquely associated. Now, already here, I have to warn you, because if you talk about polar coordinates, there is not that one single coordinate system, because there are people who use different versions of polar coordinates with corresponding consequences. So always be careful if you look up any formula using polar coordinates in the literature, or if you use data given in polar coordinates by some other people, always check which particular system they use. And you already have that in 2 dimensions, because you can also do that in a different way. I will write that down here. In the alternative way, what you can also find is that it's a r in the sine. I would now say write sine phi tilde in the r cosine phi tilde. Now, what is the difference between these 2 systems? One thing is that it has different starting points. So, okay, let me first talk about the ranges of the coordinates. So certainly, if you're in the whole space R2, then you would say R is in R0 plus, and you can choose the phi, for example, in between 0 and 2 pi, and that's what you usually find in mathematics. That's what mathematicians usually use, an interval from 0 to 2 pi. But you can use any interval that has the length of 2 pi. And you have to be aware that the starting point and the final point give you the same coordinates. So if you want to be more precise, I was not precise here, but it's not so important. If you want to be more precise, you can say, okay, let's have an integral where one boundary is included, the other one is not included. So again, any interval of the length 2 pi is okay. So you can, for example, also use minus pi to plus pi. That's because of obviously because of the periodicity of the sine and the cosine function. So I will use here that the 0 to pi interval in both cases for phi and phi tilde. So what are the differences between the red and the blue version, the cosine phi and the sine phi, and the sine phi cosine phi version? One thing again is the starting point. So for phi, equals 0, the cosine is 1 and the sine is 0. So the black version gives you a 1, 0 version. So it's a R0 version. I will still adhere to the unit circle here. So this would be the case where you have phi equals 0. Again, because cosine of 0 is 1 and sine of 0 is 0, the other version starts at the point 0, 1. So this is what phi tilde equals 1 gives you. But there is another, actually more essential difference between these two systems, and that's the way how you move through the circle. Because what happens, let's have a look at the first version here, this one. What happens if phi increases now, the cosine would decrease. Remember, maybe I can remind you of the graphs of sine and cosine. So this would be the cosine function to 2 pi, that's the cosine. And this, no, again, blue, this here would be the sine function. So if, once again, if phi increases, then the cosine would decrease and the sine would increase. So the x1 coordinate would decrease, the x2 coordinate would increase, would become positive, which means that you're here. Now the x1 coordinate is decreasing, the x2 coordinate is increasing, so you're moving in this direction. So meaning that that one here, the first one, which is the black one, which is the usually mathematical version of coordinates on a circle or circular coordinates in R2. This is the counterclockwise way of moving through it. And I can already guess what the blue version gives you. If phi tilde increases, the sign would increase, so the x1 coordinate would increase, but the x2 coordinate would decrease. We are here. We're having an increasing x1 coordinate, a decreasing x2 coordinate. So we are moving in the opposite direction here. We're moving clockwise. So these are the two differences between the two ways of doing it. But nevertheless, you can do it whatever you like. Again, my comment is look at what other people do if you use what their results or their data, and be aware of the two things that we have different starting points and we have different orientations in moving through the circle. And also take care that what people choose for the ranges of phi, the length of 2 pi is only given. You can take any interval with such a length. Now, for moving from 2 dimensions to 3 dimensions, we can use what we've just seen here, because we can interpret the sphere or ball in R3 as a union of a lot of circular disks. And I will show you that in a little animation. So you will see here now different circles at different positions. And you see that you can say the ball consists of a union of a lot of, let's say better here, the sphere consists as a union of a lot of circular lines on different levels, meaning on different z or x3 coordinates and with different radii. We can use that actually for building up now polar coordinates. So we have these different circles here which establish or which construct the sphere. And this is the versatile step for constructing polar coordinates in R3. And we do this by just looking at us taking a circle again. But this circle is now a cross section of a sphere. So I will put in there some lines by saying, okay, now that's the north-south orientation. I will simplify this by using the unit sphere. It's not actually a simplification, it's just a choosing one of the spheres. So a capital omega is how I call it, is the set of all psi in R3, which have the length 1, which have the norm 1. So omega is the unit sphere in R3. Now, what I explained is we can interpret the sphere as a union of an infinite number of circular lines. And every circular line is defined by by taking the intersection of the sphere with a corresponding parallel plane parallel to the x1, x2 plane. So in other words, we just look at different x3 or z coordinates. So we are at a particular height here. Let's say we are here now. And in that, at that level, we will have a circle line, which is here. Remember that this blue line is a cross section of the sphere. So you have here somehow the sphere going, the circular line here going around. Now, the question is, first of all, is what is the radius of that circular line? And so we will have, certainly if that is the origin here, we will have here a certain x3 coordinate, and certainly because that's yeah, I wrote I should be consistent, so it's xi1. So I have xi1 square plus xi2 square plus xi3 square equals 1. And sorry, this is a mistake. Sorry, this should be xi3 certainly. So clearly xi3 then is plus or minus 1 minus xi1 square plus xi2 square. Now, if we say once again that this should be a circular line here that we see, remember the little animation that you saw before. Sorry, there was a mistake. This needs to be a minus. I'm sorry. So if we say that this is a circular line, then certainly in that circular line that we have here, xi1 square plus xi2 square would be the radius of that circle. So we can say that r as the square root of xi1 square plus xi2 square, if you wish. So in that sense, xi3 would be simply plus or minus square root of 1 minus r square. Now we know how to parameterize that circle that we have here, namely in the sense that we say, okay, xi1 is definitely the radius times cosine phi. I'm using the mathematical parameterization, and xi2 would be r sine phi. Again, with an arbitrary choice of an interval of length 2 pi for phi. Now, what we know what r is, and we can put this in a different way. If you look at that identity, you can simply certainly also say now, well, then xi3 square is 1 minus r square, or in other words, r square would be 1 minus xi3 square. And that's just a way how you can establish polar coordinates by saying, okay, there's xi3, which I will now call t. And that is usually called the polar distance, which is a bit confusing, but that's how you find it in literature, because a polar distance, you would expect it to increase if you're away from the poles, but actually the polar distance is 0 if you're here, and it's 1 if you're here, and minus 1 if you're here. So it's not really the distance to the pole, but that's how it's called. But so if you do that here, you can say, okay, now my coordinate system would be simply the radius. And the first one, the radius, which is this here, and I will write t for xi3. And we have the square root of 1 minus t square times cosine phi. And then we have the square root of 1 minus t square times sine phi. And the last coordinate certainly is the x3 coordinate, which would be simply t. Now that's how you do it on the unit sphere. If you're at a sphere of a different radius, you have to just multiply it with the radius of the sphere, which I call r here. So that's how you establish polar coordinates in R3. Now, this might not necessarily might not necessarily be the way that you know. You might be confused if you've seen it somewhere else. Most likely, you've seen not the t, you've seen something with a theta, a latitude, and that's very easy to explain. One way is, for example, you can say, okay, let's just put the t as a cosine theta, and the theta is in between 0 and pi. Certainly, remember the cosine, we have it still up there. If the cosine is taken between 0 and pi, you get the values from 1 down to -1. So it's just moving from the North Pole to the South Pole in that case. Some other people use sine of, again, another theta, but now it's a sine, and to produce values between -1 and 1, we have to look up again up there and extend the sine. If you do that, then your theta would be in between -pi/2 to pi/2. So again, you see there is some arbitrariness, there are some options how you can choose your coordinate systems. Again, not only the fact that I could have used here instead cosine phi, sine phi, I could have used the alternative sine phi, cosine phi, which would just mean starting at a different point and moving in a different orientation. You have also here the options taking the t or replacing it by cosine theta or by sine theta with different ranges for your theta that you have in the end. So the phi that you have is usually called the longitude, and the theta is usually called the latitude that you have here in the end. I can write that down again. So the phi is the longitude, and the theta or the other theta, whatever you like, is usually called the latitude. There are also some varying notations and names for that in the literature. Now, what is that theta? If you, for example, look at this point here, then you can do a little bit trigonometry and say, okay, we have that line here, and then we have a rectangular triangle here, and then if you say, okay, that's my angle that I'm looking at, then there are a couple of things that you know. It's the unit sphere, so this has the length 1, and we know what this is here. This is the psi3 here. So the x3 coordinate of my point xi that I have. So this is my point xi now on the sphere. And then you certainly know that if I call that here theta here, then certainly by a simple trigonometry, you know that the cosine of theta would be that side here divided by the length of that side, which is just the which would just be psi of 3 divided by 1. So that's how you come up with that one way of doing it. So 0 to pi would be certainly clear. 0 to pi/2 more precisely would be clear for theta. If you're on the bottom side, you have to be aware of that you get a larger angle here down there, so you have to use some symmetry arguments to establish a triangle on the lower side, on the southern side, let's say. Now, talking about north and south, the mathematical way, once again, is what I said here: cosine phi for the x1 coordinate and sine phi for the x2 coordinate. And again, still the mathematical way is using here cosine theta, or if you want to do the workaround of avoiding this, which some people in geomathematics, including myself, do, is taking the t instead. So that's a mathematical way. Usually in applied sciences, you most commonly have the sine theta version here, and you also often find the way that the cosine phi and the sine phi are interchanged. And you also find that in applications often people take the phi with the interchange version, take it in the interval -pi to pi instead of 0 to 2 pi. And that's not very surprising if you remember your geography lessons at school. if you were talking about longitudes, you were not talking about 0 to 360 degrees. You were talking about minus 180 degrees west to plus 180 degrees or east, which is basically the minus pi to plus pi for the longitude phi. Now, it's certainly up to you if you take cosine phi sine phi or sine phi cosine phi, but that's certainly the more geographically common way of doing it. And the same is for the latitude. You also know from geography in school that people use latitudes from 90 degrees north to 90 degrees south, which is again the plus pi over 2 and the minus pi over 2 range. Okay, so much about this. Now we should use that. Now, so if you're in R3, I can write a point in R3 x1, x2, x3. Again, if you prefer, you can write x, y, z. And by that now, if you have an arbitrary point in R3, it's somewhere on a sphere around 0, depending on its distance to the origin. You can write it now as r square root of 1 minus t square cosine phi r square root of 1 minus t square sine phi and rt. I will soon talk about the alternatives. Now, what you might know is that if you calculate a volume integral in R3 on some three-dimensional domain, and if you want to change the integration from Cartesian coordinates to polar coordinates, because, for example, you're integrating over a ball or you have some rotational symmetry in your integrand, then you know that you need the Jacobian for that. More precisely, the absolute value of the Jacobian. I will show you how this is done for that particular choice, but it will also give you the other formulas for the other ways of doing it. So what we first need is the Jacobian matrix and then its determinant. So one way of writing that Jacobian would be this here. Well, let me start with T. So we first have to differentiate by R, which is very simple. I'll make this a bit shorter here. Okay. So then the next one has to be the derivative with respect to t. So we have an r, then we have the square root here. So the external derivative of the square root would be 1 over 2 times the square root. And you know we need the chain rule. The inner derivative would be minus 2t, and you can immediately cancel out the 2 here. So we're not finished. We should not forget the cosine phi in the end. So the next one is is analogous. So it's r, and then it's a minus t divided by square root of 1 minus t square sine phi, and then it's an r. And the differentiation with respect to phi is certainly easy. It's an r square root of 1 minus t square, and the cosine phi gives you minus sine phi. And then we have an r square root of 1 minus t square cosine phi, and the last one is a 0. Okay. Now, if you calculate the determinant, I would use here the fact that there's a 0. So by the Laplacian expansion theorem, it's easier to expand based on the last row or the last column. I will use the last row here. So I will start with this. This is now the third row in the first column. So 3 plus 1 is 4, which is an even number. So we get a plus t. And then we get the determinant of that 2 by 2 matrix, which is first of all a r times an r, which is an r square. So again, this one here, and this one multiplied with that one. So I have the r square. Obviously, the square root cancels out. So I get the minus t and the cosine square phi. So I will just insert the minus here, the t and the cosine square cosine square phi. So sorry. So this is that here. I've done this here, and I need minus that one. Minus, and that minus gives me a plus, and the r and the r give me an r square. And again here, if you multiply that, the square root cancels out. But I get another minus here from the minus t. So I have to change that. This is giving me now a minus. And I have a t and a sine square of phi. Again, that was the product of these two terms here. The good thing about videos, you can just stop, and if you need more time to think about it. Okay, this is the first term that was associated to that component. Now we move to that one. That's a third line, and the second row, 3 plus 2 is odd. So it's 5, so it's odd. So we need a minus now. It's a minus r. And then it's the 2 by 2 matrix established by these two components. But first, this one with that one. So it gives me an r. It gives me the square of the square root. So it's an r times 1 minus t square and a cosine square phi. So it's an r, it's a 1 minus t square and a cosine square phi. So once again, we're here and here. We've done this with that. And the remaining one, again with the minus with that minus gives me a plus. And then it's this with that one. It's an r, first of all, and it's again tries the factor with the square root, which is 1 minus t square, and the sine with the sine gives me sine square. Okay. Now, this is not very difficult. What is left to do, I could first of all collect here the t, which gives me a t square. I can collect the minus r square. So I get a minus r squared t square. Now I have that already. I have that already. I have a cosine square phi left here. And again, I have this already collected. So I have a sine square left. So cosine square plus sine square is obviously 1. I will write it down. But this is obviously 1. Okay, minus. And here I can collect again the r here, which gives me minus r square. And they have a 1 minus t square in common. And again, the rest is the cosine square phi, also sine square phi, which is again 1. So if you collect that now together, you have a minus r squared t square, and here you get a plus r squared t square, so that cancels out. So what is only left is a minus r square, and I lost something. And no, sorry, yeah. Yeah, okay, no, I lost nothing. Sorry, it's fine. You get a minus r square. Okay. So certainly, if you use the transformation formula or the substitution rule, same two names for the same thing, for volume integrals, and you want to use polar coordinates in R3, you need the absolute value of the Jacobian. So what you have to insert is the R square. Just I don't want to give a course here now on real analysis. So for details, please choose your favorite textbook on real analysis. If you don't have a favorite textbook on real analysis, get one. Okay, so but it's obviously it doesn't matter here because volume integrals don't have an orientation. So if I, for example, had interchanged the t and the phi, maybe remember that I was thinking about what would I use first. I could have interchanged the phi and the t. If I had done that, I would have taken here the derivative with respect to phi, and here that would be the derivative with respect to t, which would just be an interchanging of columns in the determinant, which just would change the signs, the sign of it. So, and certainly since it's completely arbitrary in which order I'm going through the coordinates. This should not play a role in calculating your integral. Analogously, if you calculate a surface integral on the sphere, then you would need dx by dt cross product with the x by d phi and the normal fit. And we have that already here. We have parts of it already here. This is dx by d phi, by dt, sorry. This is dx by d phi. So if you calculate the cross product, you have here the first component, and the first component first takes the second with the third, which is a 0, which is easy, minus that one with that one. So it gives you a minus r square root of 1 minus t squared cosine phi. Now the next one, the second component, after the second, you would take the third with the fourth, which gives you a minus r square again, square root of 1 minus t squared, and a sine phi. Once again, that was this one with that one. Minus the opposite version, which would be that one with that one, so, but that's a 0, so you're done. Now the third component, I have to take this one with multiplied with that one, minus again the opposite one. So this with that, again the square root cancels out. Then I have an r square again, I get a minus t and a cosine square phi. So it's again, it's a minus, I should just put the r square first, minus r squared t, so it's the r and that r. Square root cancels out the minus t here. And then we get a cosine square phi. So, and the other one, so that was this with that. Now we need minus this with that. The minus is good because this cancels out that here. So we get a plus, this with that plus, r square again. It's r square. The square root cancels out. And then we get another minus and a t. So it's again r square as we have here. And we have a minus t. It's again minus r squared t, what we get by multiplying these here and taking care of the additional minus which you get from the cross product. It's a minus r squared t that you have. But now it's multiplied with a sine square phi. I can already write this here like that. Okay. So, and again, this is 1. Now, if you calculate the norm of this is not very difficult. Because you have to just take the squares of this. If you take the square of that and the square of that, you have again common factors, which are r to the 4 and a 1 minus t square. And then you get a cosine square plus sine square, which is again 1. So that was coming from the first two components, and the last one also has to be taken as a square, which is easy. So it's an r to the 4 and a t square. So if you calculate this, you get something that you already know from above, basically what you already know from above. So it's an r to the 4, which you get here. And then you get an r to the 4 times minus t squared, and then r to the 4 times plus t squared. That cancels out. So you have only r to the 4, and the square root of that would be r squared. Remember that r is anyway non-negative. So it doesn't matter, it's anyway square. So for surface integrals, that element that you need there, that surface metric that you need there would be r squared. Now that's for that one way of choosing polar coordinates in R3. As I mentioned, it's not the only one. So I've collected here the different versions that you can use. This is again the more mathematical way, where you have the cosine phi in the first coordinate, and where you represent the t by cosine theta. So the square root of 1 minus t squared would be then the sine theta here. I will go through the very first one, that particular that you see here, how this develops. Again, the derivative with respect to r is very easy. You just take away the r and you get this one. If you differentiate it with respect to theta, that's my second coordinate, the sine theta becomes cosine theta, and the cosine theta becomes minus sine theta. And again, for phi, it's certainly easy. Cosine phi gets minus sine phi, and the sine phi gets cosine phi, and the third component is certainly 0. Again, I will expand this along the third line, the third row. So this is the third row, and the first column, 3 plus 1 is 4, is even. So we get plus cosine theta, and then you have to take this one, the upper right, 2 times 2 matrix. So you get an r square cosine theta, and the sine theta, and you get a cosine square phi, and minus the product of the other two components here, which is the minus minus, so it's a plus. Then you get an r square cosine theta, sine theta, and from both factors you get a sine phi, which gives you a sine square phi. And the other one is a minus r sine theta, which is in the third row, and the second column, 3 plus 2 is 5. So we have a minus 1 to the 5, which is the minus 1, multiplied with a minus r sine theta. And then we have to look at the first column, the third column. So it's a sine theta cosine phi with an r sine theta cosine phi, which gives r sine square theta times cosine square phi. Again, minus minus gives you plus, and then you have sine theta times sine theta, which is sine theta, sine square theta, and you have sine phi times sine phi, which is sine square phi. Then again, you have to collect the terms in the first line. Here you have cosine square and a sine square, and everything else is the same. So you can collect this and say cosine square phi plus sine square phi is 1, which gives you that here, r square cosine square theta sine theta. And it's similar in the second line. You have a cosine square phi and a sine square phi, which you can collect here, which is again 1. Then so you get the r sine square theta. And I, on purpose, put the sine theta separately, because then now you see that you have a cosine square phi, a cosine square theta and a sine square theta, which together give you this here as an r square sine theta. So that's, if you're a mathematician and you've seen polar coordinates before, that's what you've most likely seen as a Jacobian, because that's the typical mathematical way of defining it. You see that the way of using t has another advantage besides the fact that you avoid the choice of sine theta or cosine theta, is also that you avoid that getting an additional factor in calculating the integrals. You don't have, the t doesn't give you an additional factor in the integration. You just get the r square. Now, the other ones are just here. You can just stop the videos and have a look at it. So I will just go back. You see the difference. The differences are here. This is now the geographical way, let's say, where you have for the x3 coordinate a r sine theta, and it's a cosine theta in the x1 and x2 coordinate. And the result is that you get a minus r square cosine theta here. So the absolute value would be r square cosine theta, not sine theta. So it's again a thing about be careful when you use these systems, and if you look at different references, there might be differences in that respect. Now, the other two versions is now what you've seen before, but with the way that you have sine phi and cosine phi here instead of cosine phi and sine phi. I've given you the calculations here, but you can do it in an easier way than doing the same calculation again, because what you just do here is interchanging the first and the second component of the vector of the coordinate system. If you compare this one with that one, it's just the r sine theta cosine phi, which was previously the first component, and it's now the second one. It's the same for the other components, for the first and second, which were interchanged. But if you interchange these two, the first and the second component in your coordinate system, you would correspondingly interchange the first and the second row in the Jacobian matrix, and therefore also in the Jacobian determinant. So interchanging again, 2 rows in a determinant change the sign. So what you get is just the same result, except that you get a different sign in front of it. So what we had before for the mathematical version was an r squared sine theta. Now with the not completely mathematical version where you interchange the way you use the phi, gives you a minus r squared sine theta. And now the other one, where you take sine theta for the x3 coordinate, this gives you a Jacobian with r squared cosine theta. Previously we had minus r squared cosine theta. Now there's another thing which is worth to know, namely if you have a look at the derivatives that we had before here, that was our Jacobian determinant that we had. So this was the derivative of my coordinate transformation with respect to r. That's the derivative with respect to t, and that is the derivative with respect to phi. Now there's a well-known fact from differential geometry, which would, if you know that, make it very easy to continue there. If you don't know that, we can just observe what happens, what we find out about these vectors. And once again, it's a well-known fact from differential geometry that you commonly get if you don't have a too ugly or weird coordinate system. And one thing is very simple. If you look at the first column here, that was the derivative with respect to r, which is in that case particularly, especially just the division by r. And if you remember how we constructed that without the r, that is this one, with the coordinate system on the unit sphere. So we have basically just a unit vector here. And besides that, it's just a point on the corresponding unit, sphere. Because there's something very interesting about the unit sphere. If you take an arbitrary point on the unit sphere, and each of these points, every point is its own unit normal vector. So usually people write n or nu for that. The unit normal vector at the point psi is psi on the unit sphere. Now, if you have a different, if it's a unit sphere around the sphere, around the coordinate region, certainly if you have a different sphere with a different radius, but still centered at the coordinate origin, you would simply have basically the same result. It's just the fact that you have to normalize your vector. This is your unit normal vector anyway that you get here. So if you take a point on the sphere, and let's just assume it's a unit sphere. If you take a point on the unit sphere and look at its polar coordinates, and you just calculate that coordinate vector once again, so the first column of that matrix that I've just been talking about, then you would get a unit normal vector to that position. People give it a name for that. Some people call it ER, other people call it epsilon R. So it would be simply 1 minus t square cosine phi, 1 minus t square sine phi, and t. So this is just a repetition of the formula, and it means that if you're at a point with polar coordinates t and phi, then its unit normal vector at this point is just calculated this way. Now, once again, this is a common fact from differential geometry, but if you don't know that, we can just observe what we get here, because if you calculate the inner product of these 3 columns, you will find out that these 3 columns are pairwise orthogonal, which means that the derivatives of this coordinate transformation with respect to the 3 polar coordinates, these 3 derivative vectors that you get in the end, they are orthogonal vectors in R3. Now, since we found out that this is the unit normal vector to the sphere, and since those two are orthogonal to this unit normal vector, they must be tangential to the sphere. And since they are orthogonal to each other, they are an orthogonal basis to the tangential plane at the point associated to the polar coordinates t and phi. So they're an orthogonal basis, but not yet an orthonormal basis, because these 2 columns on the right-hand side, they are not normalized. But we can easily calculate the norm of them. but just taking the square of the components and summing it up. First of all, if you take the square of that and that one, you observe again that we have a cosine square phi plus sine square phi term. So we get together r square, and then we have a t square divided by 1 minus t square. That's what both have in common, and one has the cosine square, the other one has the sine square, both are phi. So if you sum it up, you get this. And the third component gives me an r square, which I already write as an r square times 1 in that way. And then if you sum it up, you will see that it's simply an r square times 1 over 1 minus t squared. Okay, because it's an r squared t squared minus r squared t squared, is what you get here. So the norm of the vector would be r over square root of 1 minus t squared. So if you divide it by the norm, so we have to divide, divide, or it's easier to say multiply. Multiply with square root 1 minus t squared divided by r. So because this is the square of the norm, right? So if you divide it by the norm, to multiply with that one, you get a normal vector, which is easy here because just the r cancels out. And the square root here means it cancels out here, but you get the square root in the end here. So what you get in the end, what is left is the minus t and the cosine phi here, and the minus t and the sine phi, the rest cancels out. So we get a vector which you can call et or epsilon t. So once again, it's an r and the square root cancel out. It's a minus t cosine phi and the minus t sine phi. And the last component, the r cancels out, but we have to multiply it with the square root of 1 minus t squared. What do you get in the end? Now it's similar for that one here, for this component. It's very easy if you take the squares of all that and you sum it up. Certainly you get again a sine square plus a cosine square phi, and you get an r square times 1 minus t squared. So you have the norm of that here, the norm of this vector here, is obviously r times square root 1 minus t squared. You can also just say if you take that in front of the vector, your vector would just be minus sine phi and plus cosine phi, which is definitely a unit vector. So you have to divide it by divided by r and the square root of 1 minus t squared, which gives you simply minus sine phi and cosine phi. That's very easy. And that's called E phi or epsilon phi, and this is just minus sine phi and cosine phi and there. So if you prefer the other coordinate systems, you can do that in a similar way. You get similarly vectors, then maybe an E theta, not an ET, or epsilon t. If you have a closer look at these vectors, which you get in the end, then you will find out that so that's a sphere now with the latitudes here and the longitudes here. Now the epsilon t vector, let me maybe start with the epsilon phi vector. The epsilon phi vector obviously has not have a component in the third direction, so it's always parallel to the x1, x2 plane, and actually pointing towards east. So you get easily the eastern direction. So again, at the point on the unit sphere given by the polar coordinates t and phi, you can calculate the eastward direction by that vector and you easily get the west direction. So that would be epsilon phi. I use the epsilon here. And for the ET, it's the north direction, what you get in the end. Now, what you might have observed when I was normalizing the vectors, I could have certainly also multiplied them with -1, so taking the opposite direction. And the same can happen if you, again, have different coordinate systems. You might get minus these vectors instead. So you might not have the east direction, but the west direction, and not the north direction, but the south direction. So these are very helpful, for example, if you have a vector field on the sphere, like, for example, a ocean current or a wind field that you're looking at, or a magnetic field, talking about geoscientific applications, because you can easily then decompose that vector field on every point on the surface. You can easily decompose it into the normal part by projecting it on the epsilon r vector, and decompose and the tangential part, which you can again subdivide into a west-east part and the north-south part, which is for some of geographical applications certainly very valuable. Okay, that's basically all I want to tell you about polar coordinates. I hope you learned something. I hope it became interesting for you. And I want to give you, again, the comment that I want to give for all the videos I'm producing like that. An internet video can never replace a good textbook. So look at your books, at your favorite real analysis book, talking about polar coordinates, coordinate transformations in general, what you can do with that, how you can use it for integrations of volumes or on surfaces. What is that good for? And if you want to know more about the last things I told you just here about these epsilon r, phi, and t vectors, look at the more geomathematical literature. Also here you will find more information about that. Okay. I hope to see you. I hope you will see me. I will not see you. I hope you will see me in some other videos. And if you have comments on my videos, you're certainly free to send me an email. Thank you very much for listening.